Hey everyone, continuing with our integration of trigonometry squares, we're going to look at the 4, or actually rather 3 remaining trigonometry squares that we haven't talked about. Namely, well, we've already talked about this, but I'm just going to include it here. Secant square x, tangent square x, cosecant square x, and lastly, cotangent square x. So we already know that, well, the integral of secant square x is basically tangent x plus c, right? So that one's already a given. But what about tangent square x? So similar to sine square x and cosine square x, you cannot directly integrate this, right? Because you'll be introducing a secant square x term using the power rule. As such, it's invalid to use the power rule. So again, just like sine square x and cosine square x, you need to find another way of representing or expressing tangent square x such that it will become integrable. So let's find some ideas, right? So let's find the identity function. So identity relationship, we have 1 plus tangent square x equals to secant square x. Okay, then I can express tangent square x equals to secant square x minus 1. Then you notice you can integrate secant square x to give you tangent x. You can also integrate minus 1 to give you minus x. As such, we are able to integrate tangent square x. So we integrate tangent square x dx as integrating secant square x minus 1 dx to obtain tangent x minus x plus c. And therefore, the integral of tangent square x is tangent x minus x plus c. Now we move on to the other pair, cosecant square x. So if you recall from a differentiation, if we were to differentiate cotangent x, we will get back minus cosecant square x. As such, integrating cosecant square x would give us minus cotangent x plus c. Because by differentiating minus cotangent x, you get minus cosecant square x equals to positive cosecant square x. And now we look at cotangent square x. Similar to tangent square x, sine square x, cosecant square x, you are unable to integrate cotangent square x directly because if you're going to use the power rule incorrectly, you'll be introducing a new cosecant square term. As such, we have to do the same thing, find a way to express cotangent square x in the integrable form. Let's take a look at the identity relationship again. 1 plus cotangent square x would give us cosecant square x. As such, we have cotangent square x equals to cosecant square x minus 1. We can integrate cosecant square x as seen from just now. We can also integrate minus 1 to minus x. As such, we will integrate cotangent square x in the form of integrating cosecant square x minus 1, which would give us, well, simply, I think you can actually work this out yourself, minus cotangent x minus x plus c. And then we will arrive at this general formula, again, where we have fx as a linear algebraic function. So we have secant square fx, and I think you've seen this before. So let me just put this here y, and here integral y dx. So we have tangent fx over f prime, which is a plus c. We will have tangent square fx, which will simply be 1 over a secant, 1 over a tangent fx minus x. So this is unaffected by the 1 over a because we're integrating a constant, as you remember from just now. Then next up, we have cosecant and cotangent. So looking at cosecant square fx first, we would have minus cotangent fx over a, again plus c. And lastly, we have cotangent square fx, which would give us minus cotangent fx over a minus x, because again, you're integrating a constant. If you remember from the identity relationship, you'll give you back minus x instead of minus x over a. Therefore, this is the general formula for the remaining 4 trigonometry squares, or actually remaining 3 trigonometry squares. And I'll end off with an example. So for example, I want to integrate, let's say, tangent square 2x plus 1. Again, you don't have to memorize this formula, all right? You just go through the steps. So tangent square and cotangent square, you must relate it back to your identity function, which is secant square. So I relate it to, well, I get back secant square 2x plus 1 minus 1 dx. And then now I integrate secant square, it becomes tangent 2x plus 1. Don't forget to divide by the derivative inside, then you must minus by a x dx. Same thing for cotangent square. Let's say I have now 2 minus x instead dx. So it's the same as integrating cosecant square 2 minus x minus 1 dx. Sorry, there's no dx here. Oops, it's a plus c. Now, integrating cosecant square 2 minus x, I get back negative cotangent fx, right? So I get cotangent 2 minus x. Now, divide by a, which is minus 1. So minus, I had minus cotangent 2 minus x over by minus 1. So I basically get back positive cotangent 2 minus x. Then minus 1 integrated is minus x, so no change to that. And finally, your plus c. So yes, there we have it, the remaining squares, remaining trigonometry squares and their integrals.